Welcome back to this series on topology. In this video, we'll be discussing closed subsets, as well as the closure and interior of arbitrary subsets of a topological space. You can find a playlist containing all of the videos in this series by clicking the info card that should appear now. Alright, let's get started. Last time we gave the definition of a topological space, which is essentially just a set X together with a collection of subsets of X which specifies the topology. So this topology T is a subset of the power set of X, so it just consists of subsets of X. And we call X a topological space, and this T is the topology on that space. Remember that we also called the elements of T open sets. And these need to satisfy certain axioms. So the first axiom was that the entire space X and the empty set need to be open. The second axiom was that the open sets are closed under finite intersections. And the third axiom was that the open sets need to be closed under arbitrary unions. So that's first, X and the empty set are contained in the topology. Two, we have closure under finite intersections. And third, we have closure under arbitrary unions. With that brief review out of the way, let's turn to what we're actually going to be talking about in this video, which is the counterpart to open sets, which are called closed sets. So the definition of a closed subset is as follows. If X is a topological space, then we call a subset of X closed if its complement is open. Another way of phrasing this in terms of the topology T would be to say that a subset is closed if its complement is contained in the topology T. If we represent our space X as follows, and we think about some subset of X, so let's consider this blue subset of X, and let's call that A, then the question of whether this is closed depends on what the complement of A is doing in terms of the topology on X. Hence, to determine if A is closed or not, we have to consider its complement in X, so that's X minus A, and this would be this red set. And if this red set is contained in the topology, so is open in the space X, then A would be closed. Notice that this definition is not saying that the subset A is not open. So it's possible for a subset to be both open and closed, or neither open nor closed. So when we're thinking about closed subsets, we're thinking about them being dual to open sets under complementation, but not under logical negation. So it's a common trap to fall into where you think a set is closed means that it's not open, but in fact that's not always the case. So if we suppose in this pictorial example that this red set is an element of their topology, then A would be closed, but A could also be at the same time an element of the topology. There's nothing stopping that from happening. So in this case, A could be both open and closed. On the other hand, the opposite could occur, so the complement of A could be not contained in the topology, so A would not be closed, but also A itself could not be contained in the topology, in which case A would also not be open. Now this duality between closed and open sets under set-theoretic complementation has some immediate consequences. Namely, we can convert the axioms for the topology into statements about closed sets instead of open sets. I'll make two columns here. The column on the left is talking about open sets, and then the column on the right will be talking about closed sets. Now we phrased our axioms for a topological space in terms of open sets. So the first axiom was that X and the empty set are open. Then we had closure under finite intersections. And closure under arbitrary unions. We can now think about what these points mean for closed sets. So the first point implies that the empty set and X are both closed. Why is this? Well, the complement of the empty set is the entire set X, and that's open by our axiom. So by definition, it means that the empty set is closed. And similarly, the complement of X is the empty set, which is open, so X is closed. Now the second point translates into the fact for closed sets that closed sets are closed under finite unions. That is, if we have a finite collection of closed sets, then the union of that collection is again closed. The reason this statement is true is because of the De Morgan laws from set theory. Remember that if we take the intersection over the complement of some sets, which I'm now writing with this superscript C to indicate the complement to make this formula look a little nicer. So we're first taking the complement of all these AIs and then taking their intersection. By the De Morgan laws, that's the same thing as taking the complement of the union of all of these sets. So we're first unioning all the sets and then taking their complement. The proof of this identity basically boils down to the fact that the De Morgan laws hold axiomatically for logical disjunction and conjunction. So if we have the negation of a disjunction, that's the same thing as the conjunction of the negations. So here we have, sort of as an example, we would have not A and not B is logically equivalent to not A or B. And you need to use this conversion in the proof that these two sets are equal. In any case, what the De Morgan laws are saying is that if we take the complement of a union, so that's the lower way of expressing this set, then that's the same thing as taking the intersection of the individual complements of the sets. Now suppose we have some finite collection of sets AI which we know to be closed, and we want to determine if their union is also closed. Now, by definition, we need to see if the complement of this union is open. That would tell us that the union is closed. So we're looking for the complement of the union of these AIs, which is exactly the expression in the bottom part of this De Morgan formula. But now the De Morgan law is telling us that this is equal to taking the intersection over the complements of the AIs. But because each AI is individually closed, it means that its complement is open, and now we're taking a finite intersection over these open sets, which is by the axioms of a topological space, again open, and this shows that the original set on the bottom, which we were interested in, is open, and hence the union of the AIs is closed. Observe that this argument wouldn't have worked if we'd taken an arbitrary collection of AIs, because then we would have gotten, by the De Morgan laws, instead of this finite union, we would have gotten an infinite union, and in that case, we can't conclude that the infinite intersection over the AI complements would again be open. Now, a very similar argument shows that the fact that the open sets are closed under arbitrary unions implies that the closed sets are closed under arbitrary intersections. So we can see that there's this duality between the open sets and the closed sets under complementation. Let's move on to some examples. So as a first example, let's consider a closed interval in the real line. Now, in order to show that this interval is indeed closed, we need to consider its complement in R. So that's R minus the closed interval a, b. Now this is equal to the ray going from a to minus infinity. So that's open on one side, unioned with the ray going from b to infinity that's open at b. Now we know that individually, both of these sets are open, and so that their union is also open. Hence, because the complement of this closed interval AB is open, it means that the closed interval is in fact closed according to our definition, which is good. Our next example is that of a closed ball in a metric space M. So by definition, the closed ball of radius r around X is just all the points y in the metric space such that the distance between X and Y is less than or equal to the radius r. Pictorially, if we have some point X and some radius r, we're just considering all points y that lie in the circle of radius r around X. So that's this yellow shaded region, and it includes the boundary around the circle because we have the less than or equals. Now to determine if this set is closed in the metric space M, we need to consider its complement, which is everything that lies outside of it. If this complement is open, then the yellow set would be closed. Now what does it mean for the red set to be open? Well, we're considering the usual topology on the metric space, so by definition, it means that if we take any point y in the set, then we have to be able to find a small ball of radius epsilon around that point that still completely lies within the set. And if we can do this for any point in the red set, then after the red set is open, which by definition means the yellow set is closed. Okay, so what do we know? Well, we know that the distance between X and Y has to be strictly greater than R, because Y is not contained in the closed ball of radius R around X, so it has to have a distance from X that is strictly greater than R. But this implies that, well, the difference between this distance and R is strictly positive. This quantity here is the stretch I'm drawing in blue in the sketch. And now our picture suggests that we can just choose epsilon to be this quantity. To see that this works, we now need to show that any point in the ball, the open ball of this radius epsilon around Y is not contained within the yellow set. So we take some point Z in the open epsilon ball around Y, and now we need to show that it's not contained in the yellow set. The way we do this is we use the triangle inequality. So these stretches I'm drawing in white represent distances, and by the triangle inequality, which holds, well, it's an axiom in any metric space, we have that the distance between X and Z plus the distance between Z and Y is greater or equal than the distance between X and Y. But now we know that the distance between Y and Z, well, this distance is strictly less than epsilon because Z is located in the open epsilon ball around Y. So in fact, we can replace this term in the inequality by epsilon, and we'll get a strict inequality in the same direction. So that's dxz plus epsilon is strictly greater than dxy. Now we can subtract epsilon on both sides of this inequality. So we do minus epsilon on this side and get rid of the epsilon on this side. And we have this strict inequality for the distance between X and Z. Now we remember that we defined epsilon to be the distance between X and Y minus R. So in fact, the right-hand side of this inequality is just the distance between X and Y minus the distance between X and Y minus R. And this is equal to R. And now we've shown that the distance between X and Z is strictly greater than R, which means that Z is not contained in this closed R ball around X. Therefore, the open epsilon ball around Y is completely contained in the complement. And this shows that the complement, this red set, is open, and that shows that the yellow set is closed. Our third example is somewhat simpler to prove. It says that any subset of a discrete space is closed. Why is this the case? Well, if we take any subset in the discrete space, then we need to look at its complement and see whether it's open. But recall that the discrete space is, well, the topology where we include every set to be open. So the complement of any set is open, which means that any set is also closed in the discrete space. Notice that this is a case where every set is at the same time open and closed. So this is an example of the fact that being closed does not imply that a set is not open. As you can see, dealing with closed sets is pretty much just playing around with set theoretic complements, and one has to just watch out that one keeps track of where points are located and where they're not supposed to be located. So we've seen that in a topological space we have this topology which describes the open sets of the space, and we have the closed sets which are the complements of the open sets. Now, one question we can ask is if we have some arbitrary subset in our space, which doesn't necessarily need to be open or closed, can we somehow obtain a closed set or an open set from that subset? And it's this question that leads to the following definition. So if we have some arbitrary subset A of our space X, then we define its closure in X to be the following set. So we write this A bar, and it's just the intersection over all the sets B in X that contain A and that are closed. Let's draw a picture. So we have some arbitrary set A, and this doesn't necessarily have to be an open set or a closed set. And now what we do is we look at all the closed sets in our space X that contain our set A. We know, for example, that the entire space X is closed, and obviously it contains A, so that's one of the sets. But then there might also be a bunch of other closed sets, like this B, that contains A, and then there might be an even smaller one inside here, C, and so on. And now to get the closure of A, we look at the intersection of all of the closed sets that contain A. In our picture, that would be the region I'm shading in now. Now, because of the way we've defined the closure, it means that the closure of A is the smallest closed set that contains A. So we need to justify this claim. Well, why is the closure closed? Well, we saw in the previous slide that the intersection of an arbitrary collection of closed sets is again closed. And that's exactly what we're doing here. We're taking these closed sets B that contain A, and we're taking their intersection. So the result will again be a closed set. So in particular, this closure of A is a closed set. Why is it the smallest closed set that contains A? Well, suppose we have some set that's closed and contains A. Then it will be included in this intersection, and hence the intersection will be a subset of that set. Therefore, the intersection is the smallest closed set containing A. In a similar way, we can also derive an open set from an arbitrary subset A as follows. So we define the interior of A in X as the set A with a little circle on top, and we kind of do the dual to what we did before. So we take the union over all subsets C of X that are contained in A and that are open. So in this case, if we have our set A, then what we're looking at is these subsets C, which are open sets in our space X and that are contained within A. So there might be many of them. This might be some subset D. And the interior is now the union over all of these subsets. Notice that because we're taking a union over a collection of open sets, the result is again open, so the interior of A is an open set. Moreover, it's the biggest set that's open and contained in A. This is because if we have any set that's open and contained in A, it'll be contained within this union, and that shows that the union is the biggest open set that is contained in A. Maybe an analytic way of thinking about the closure and the interior would be thinking about them as approximating A by closed sets and open sets respectively. So the closure of A would be the best approximation of A by closed sets from the outside, and the interior of A would be the best approximation of A by open sets from the inside. With these definitions in place, it's now also possible to define the exterior of A, and we say that the exterior of a set A is just the complement of its closure. If I draw A sort of suggestively with this dotted line to suggest that it's like an open set of R2, then its closure would be the set that we obtain by closing off this set. So this red thing is the closure of A. And now the exterior of A is the complement of this closure. So just to be clear, the closure includes all of this shaded region. And now the complement would be anything that's outside. And that's the exterior of A. Notice that because the closure of A is a closed set, its complement, the exterior, is an open set. Finally, we can also think about the boundary of a set A, and we define the boundary of A, which we denote del A, as the complement of the interior of A unioned with the exterior of A. This will again require a picture, so I'm going to draw A with this dashed line. And now the interior of A is something that lies, well, it's the largest open set that's still contained in A. So the blue thing would be A interior. And now the exterior of A is the complement of the closure of A. So it would be somewhere out here. So this is exterior of A. And now we've defined the boundary to be the complement of the exterior unioned with the interior. So that's everything that's left over once we take away this red exterior and the blue interior. And this would be something like this that I'm drawing in pink now. So the pink thing is the boundary of A. As this picture illustrates, we can think about the interior of A as the inside of the set A, the exterior as being the outside of A, and the boundary as being, well, the boundary of A. And in many cases, this intuition is correct. For example, if we look at sets in R2, and we consider the epsilon ball, so that's the open epsilon ball around some point x, then it's the case that the interior of this open epsilon ball is the open epsilon ball itself. The closure of this open epsilon ball is the closed epsilon ball around x, and, well, the exterior is just the complement of the closed epsilon ball. And now the boundary is exactly all the points that have distance from x equal to epsilon. So the boundary is in fact a circle of radius epsilon around x. Often it's useful to think about what it means for points to be in the interior or the closure in terms of neighborhoods around those points. And the following proposition has a bunch of characterizations of the sets we've just seen in terms of neighborhoods. Now, because there are many parts to this proposition, I'm not going to prove every single one, but I'll try to prove some representative ones, and then I'll leave the rest as exercises. Now, the first point in the proposition states that y is in the interior if and only if y has a neighborhood that is contained in A. For this, recall that a neighborhood of y is just an open set that contains y. The proof of this is just applying the definition. So we have that y is in the interior of A, and this is by definition the union over all subsets B of X, where B is contained in A and B is open. Okay, so y is in this set, the interior of A, which is this union, and by definition, a point is in the union if and only if it's contained in one of the sets that's being unioned over. So the definition of a union says that there exists some subset B of X such that y is contained in B, and now because B is part of this union, B is a subset of A, and also B is open. But now these two things, namely that y is in B and B is open, means that, well, B is a neighborhood of y. So that's if and only if B is a neighborhood of y. Now this other point, that B is contained in A, is also what we wanted. So B is a neighborhood of y, and it is contained in A. And now if we look at our sequence of equivalences, then it's saying that y is in the interior of A if and only if there exists some neighborhood B of y that is contained in A, which is exactly what we wanted to show. The next statement is similar, and it deals with the boundary of A. So it's saying that y is contained in the boundary if and only if every neighborhood of y contains a point of A and also contains a point of the complement of A. I'm going to skip the proof of this, but I'll draw a picture to illustrate what's happening. So if we have some set A, and what I'm drawing in white is supposed to be its boundary, then if we look at some point y in the boundary, this characterization is saying that this point y is in the boundary if and only if every neighborhood of y, so that's an open set that's containing y, for example this red set, if and only if this red set has both a point that's located inside A, so this would be A, and the point that's located in the complement of A. If this fact holds for every neighborhood of y, then y is in the boundary. And conversely, if y is in the boundary, then this fact holds for every neighborhood of y. The next part of the proposition deals with the closure of A. So it characterizes the closure by saying that a point y is in the closure if and only if every neighborhood of y contains a point of A. Notice that this part C is somehow dual to part A. So in part A we had the equivalent condition being that y has a neighborhood that is contained in A, and in part C we're saying that every neighborhood of y contains a point of A. So we have existence replaced by universal quantification, and also instead of being completely contained in A, we just require there to be at least one point of A inside every neighborhood. So I'm drawing here the closure of A, and now it's saying that some point y is in this closure, for example on the outside, or it could also be on the inside of the closure, if and only if every neighborhood of y contains some point which is also located in A. So A might be the orange set I'm drawing now. The proof here is very similar to the one I gave before. So it's basically, again, just looking at the definition. You have that the closure of A is equal to the intersection over all C contained in X, such that A is contained in the set C and C is closed. Now, by the definition of the intersection, y is in this intersection if and only if y is in every c, well, in the intersection. So for all c that are, well, they contain A, and also they have to be closed. That's the condition on the sets in this intersection. Now suppose that y would have some neighborhood that is completely disjoint from A. So that's the negation of the statement on the right. So we're supposing that y is contained in some open set, that's the neighborhood of y, that would be completely disjoint from A. So I'm drawing this in blue. So maybe I call it N. Now by definition, this set N is open, which means that the complement of N is closed. So the complement of N is everything outside of N, which I'm drawing in red. Now because we've assumed that N is completely disjoint from A, this complement of N contains the set A. So N complement is a closed set that completely contains A. Moreover, we also know that the complement of N does not contain Y, because Y is contained in N. So this red set, N complement, is a closed set that completely contains A, but does not contain Y. But we assume that Y is contained in every set that's both closed and contains A. So that would be a contradiction. So in fact, such a set N can't exist, and the fact that Y is contained in every closed set that contains A implies that every neighborhood of Y must contain a point of A. Now, this argument works in both directions, because suppose that every neighborhood of Y contains a point of A. Now assume for the sake of contradiction that there is some closed set that contains A, but that does not contain Y. Well, then the complement of that closed set would be open and a neighborhood of Y. Moreover, because the original closed set contains A, the complement, so this neighborhood of Y, would be disjoint from A. But this contradicts our assumption that every neighborhood of A must contain a point of A. Hence, we've shown this equivalence, and in total, we've shown that Y is in the closure if and only if every neighborhood of Y contains a point of A. The next part of the proposition is a formula for the closure in terms of the boundary and the interior of A. Here I will again skip the proof, but I'll sketch what's happening. So what this equation is saying is that if we have some set A and we look at its closure, then this is equal to either we look at the union of A and its boundary, so in blue would be A, and then we would have, say in pink, we have the boundary, so it's saying that A union with its boundary is the same thing as the closure of A. Or instead of taking A unioned with the boundary, we could actually just take the interior of A unioned with the boundary. And that's also equal to the closure of A. So in essence, this equation is saying that the pictures we're drawing kind of make sense because we can think of the closure as being, well, the inner part of A unioned with the boundary. The next part of the proposition we've already shown, namely that the interior of A is open and so is the exterior of A, while the closure and the boundary of A are closed. Remember that the fact that the interior is open just follows from the fact that it's a union over open sets, and the fact that the closure is closed follows from the fact that it is an intersection of closed sets. And the way we've defined the exterior as a complement of a closed set means that it's open, and the boundary is the complement of an open set, and so it's closed. Finally, we have 2 points in the proposition which express equivalent conditions for a set being either open or closed. The first one states that a set A is open if and only if A is equal to its interior. And this is also equivalent to the fact that A contains none of its boundary points. Let's give a quick proof. For this, we just need to recall that the interior of A is defined as the union over all sets B that are subsets of X, where B contains A and B is open. Now assume that A is an open set, then we know that, well, A is a subset of X and A is contained in A. This implies that A is actually a part of this union, so that the interior of A contains A. Again, this is just because if A is open, then A is an open set that is contained in A, hence it needs to be contained in the union over all such sets. On the other hand, because the interior of A is a union over sets that are contained in A, it itself is also contained in A. So now, together with the fact that the interior of A is contained in A, because it's a union of sets that are all contained in A, this implies that A is equal to the interior of A. So with that, we've shown this implication. For the next implication, we have to recall that the boundary of A is defined as the complement of the exterior of A unioned with the interior of A. Now, if we assume that A is equal to its interior, then we have that this whole thing is equal to the exterior of A unioned just with A. Okay, but now we're done because we see that the boundary of A is the complement of a union which includes A. So by definition, any point in the boundary cannot lie in A. Hence, A does not contain any of the points in the boundary. So with that, we've shown this implication. Now, the implication that if A is equal to its interior, then A is open is straightforward because we've already showed that the interior is an open set, so if A is equal to that open set, then obviously A is open. So the only implication we still have to prove is that the fact that A contains none of its boundary points implies that A is equal to its interior. Thus, let's suppose that A is disjoint from its boundary. And we want to show that A is equal to its interior. Now, by part A of this proposition, it's sufficient to show that for any point in A, there is some neighborhood of A that is completely contained within A. Let's suppose, for the sake of contradiction, that this is not the case. So this means that we assume that for all neighborhoods U of some point y in A, we have that U is not contained in A. But this means that there's some point Z in U where Z is an element of the complement of A. Thus, for any point in A, we have that all neighborhoods contain a point of the complement. But now we also know that Y is a point of A. So each neighborhood of a point Y in A contains both a point in A and a point in the complement. And this was another one of the statements we had earlier in the proposition, namely that a point is in the boundary of the set A if and only if every neighborhood of it contains both a point of A and the point of the complement of A. So together this implies that Y is actually in the boundary of A. But now this is a contradiction because we have at the same time that Y is in A and Y is in the boundary of A, but we assumed that the boundary of A and A were disjoint. So in fact, there has to exist some neighborhood U around A that is completely contained in A, which means that A is actually equal to its interior. And this proves the final implication, and so we're done with this part of the proof. The final part of this proposition is the corresponding statement for closed sets, and it states that a subset of X is closed if and only if it's equal to its closure. And this is also equivalent to the fact that the set contains all of its boundary points. The proof of this statement is pretty much dual to the previous one, where one just considers the complement of everything. Before concluding, I'd like to remark that this statement F and G, they're really useful in practice. So if we combine the statement F with statement A, then checking for a subset being open is the same thing as showing that for any point in that set, we can find a neighborhood around that point that's completely contained in the set. And similarly, if we want to show that a set is closed, then we can just take an arbitrary point in its complement and show that there's some neighborhood around that point that's completely contained in the complement. With that, I'm done with what I wanted to say in this video. So we've seen the definition of a closed set, of the interior of a set and the closure of a set, as well as the exterior and the boundary of sets. And then we've seen, well, in this lengthy proposition, a bunch of different ways that all of these different notions are related. This is a lot to keep track of if you're seeing it for the first time, but we'll be using parts of this proposition throughout the course, and so with time one gets used to dealing with these different definitions. Next time we'll be moving further in this direction by defining what it means for sequences to converge in a general topological space. And we'll see that we can also relate the limits of convergent sequences to these notions we've defined in this video.